Okay, let's get started. I'm going to talk for a while about graphs, and I'll be raising some of the themes that were already raised in the discussion. Nothing wrong with that. Here's an outline of the kinds of things I'll do. I'll try and focus on the kinds of graphs that we normally make, and that maybe consider some of the mistakes that we would normally make while we're producing our graphs. So I want to start again with the question, why do we make graphs? And the answer is because they can change the world. And this is a good example. I wonder if maybe that can be lowered a bit. It's already watching this out. So this is a graph, a sort of colored version of a graph that was created by Florence Nightingale, who presented the data to the British Parliament to convince those that made decisions about war that most soldiers don't actually die of bullets, but rather that most soldiers die of disease. And that country that could control the spread of infectious disease would win the war, basically. And not only did she campaign for better treatment of soldiers, but she took this campaign to the public as well, and agitated for better public health in general, and we probably are all the beneficiaries of this. But graphs can be really effective ways of communicating this. It's visually more arresting than a table of numbers, for example. This is, I don't know what it is, it's an exploded pie chart or pie graph. You wouldn't see this anymore, so it's not necessarily the most effective, but it worked for its purpose at the time. But when we make graphs, what we're trying to do is detect patterns in data, see stuff. Usually we're creating graphs over and over and over again on the computer to see what kind of pattern we see in the data, but then we also want to turn this around and communicate this to others. So how best to do that? Here's the colorized version of the best statistical graph ever made. And when I first saw this, that was according to Edward Tufte, who sort of started the field of information graphics as a discipline. He wrote this slim book, and many adhere to it. It was certainly a starting point for thinking about graphs. And it's kind of why I do this at this stage in the course. We all sort of used Excel in the past, maybe to create graphs, but didn't think very deeply about what graphs are, what they're for, and how best to communicate not just to others, but even to ourselves. So I'll admit that history was my least favorite subject when I was in high school, and one reason might have been that there were no graphs in my history book. that it's true, it takes a minute to get the hang of this graph, which could probably be simplified, but if the width of this line is the number of soldiers, you get a very good impression of what the hell happened to Napoleon's army when he crossed the Russian border and came back. This was just a dismal failure, and the scale of the mortality is staggering. It produces almost a visceral effect when you realize how many people died during this campaign. So graphs can do that. And the other thing that's cool about this graph, and that I think that we should all try to emulate when we create and present our own graphs, is to think, when you present a graph, you don't want the viewer to go, "What?" or "Huh?" You want the viewer to go, "Oh, I get this," and so it's a good target for constructing graphs and thinking about what works and what does not. So Tufte had sort of an idea of how you could produce that effect, graphical excellence, and he has this sort of line which many adhere to as they would the Bible, and that is, graphical excellence is that which gives to the viewer the greatest number of ideas. Not necessarily the number of data points, but that can help. But ideas in the shortest time with the least ink in the smallest space. And I think that's not a bad guideline, it's not an absolute rule to think about. So most of our graphs are a little more pedestrian than that. I've just produced a histogram. Here's a strip chart. But these are the kinds of graphs that we normally create with our data, and we try to use them to show patterns in the data. So give to the viewer the greatest number of ideas in the shortest time. And there are really two kinds of graphs that we make when we analyze data. One is just to show distributions, what the frequency distribution looks like. You know, this vividly shows a frequency distribution. And then the other is to show associations between variables, or equivalently, the differences between groups, treatment effects. So here's a graph that attempts to do that. And so the job that is ours when we analyze our own data is, how do we actually accomplish that best? So here's sort of my list, our list. We took this from the Whitlock and Schluter book, which is sort of a distilled version of the total number of guidelines that Wiener presents. But I think that that these four principles will steer you in the right direction. And the first one, which you'll read over and over again, is that you should show the data rather than hide it. The second is that you should make patterns in the data easy to see. Make the viewer go, oh, and not, what? Third, be honest, so don't distort the magnitudes. Actually, tell it like it is. And then four is just kind of an add-on to minimize clutter. Make the elements of the graph as clear as possible. And I'll show you examples of how this can be achieved. So some of this is from various papers, and there was a nice paper recently in PLOS Biology where Weissenberger et al. Tried to sort of review, to take us to task for the kinds of graphs that we produce, and then to try to recommend practices for producing graphs that are, you know, maybe a lot better than the typical graph that you find. So here's an example of how you would, above all else, show the data. And so these two plots, or really three plots, show the same data, or they're based on the same data. And maybe A is the kind of plot that I think you would most often see if you picked up a publication in science, nature, ecology, letters, you name it. But very frequently, differences between groups will be summarized by a bar, and some quantitative measurement will be summarized by a bar and a standard error. But a disadvantage of this style of graph is that it doesn't show the data. And so here's another depiction of exactly the same data that were used to create this graph, but this time the data are shown. And in this particular example, you know, there's only 3 to 5 data points per group. Like, nothing stops you from showing. This is not visually confusing. And it does give to the viewer ideas that are hidden when the data themselves are hidden. Like, oh, there's an outlier. This makes me rethink my view of, you know, where this mean or median lies. It also allows us to look at the data and go, oh, there's only 5 points per group, which is surprisingly difficult to get from this kind of a graph, unless maybe you add numbers, you know, and then suddenly you're starting to add more and more elements. And somehow the number 5 doesn't convey it in the same way as 5 dots. So this is called a strip chart, and we'll be doing them in the workshop in R on Thursday. So here's another example of showing the data. Now, in some cases, the data are more numerous, and it becomes crowded to start to show all of the dots. And there are other ways of doing this then, by showing the data with visual summaries of characteristics of the data. So in a box plot, the median is shown here, the quartiles are shown here, and then these antennae capture most of the range of the data points, and then there's things called outliers, which are more than 1.5 times away from this median as the width of this box. There are conventions about these box plots. Basically, these dots are just simply far away relative to the rest of the data points. But here's how such data are still most likely to be presented in a publication, which is that there will be bars and there will be standard errors. And the bars themselves, in this case, give you absolutely no information that isn't already contained in the dots at the top of the bar. So you're spilling a lot of ink without actually showing anything new. And the complaint about this is that it hides the data, so it doesn't give you as many ideas. There's far less information in this, and yet far more ink than in this plot. And now we're getting the impression that, hey, these distributions are skewed. There might be some extreme observations, and so on. So the second rule, make patterns in the data easy to see. And this is again thinking about the target, that when you show a graph to a viewer, it should make them go, oh, instead of, what, huh? So here's a huh graph, even though the pattern itself is super cool. So it was a paper published by Moore et al. In which they demonstrated, they showed that not a perfect correlation, but a surprising similarity in the distribution across Africa in the species diversity of birds and the cultural diversity of languages of the people that live in these areas. So it's kind of cool, gets you thinking, why should cultural diversity be highest where bird species diversity is highest? And so on. And the way, I mean, they demonstrated this in a number of ways, but I chose one of their graphs. And so they've got a little guide here. So where language richness is high, it's sort of deeper purple compared to black, where it's low. And black is also where bird species richness is low, but it's green when it's high. And then white means both are high. And you know, when I read this paper, I looked at the map, I looked at the key, I looked at the map, I looked at the key. I'm just not seeing very clearly how language richness and species richness, bird species richness are associated. And you know, even though it would take a little more space, maybe a separate map of each of them would have conveyed that to me much more effectively. So even though this is really interesting data, it just took too long for me to understand, and still does. I still can't see it clearly. 3, draw graphical elements clearly, minimizing clutter. So Tufte is on about minimize the data to ink ratio and within reason. So again, keep your focus not so much on the rules, guidelines, but focus on the objective of the graph. What exactly is it trying to convey? Does it do it effectively? And maximizing the data to ink ratio is one way of doing that. So I created this graph. This is using default options in ggplot, a strip chart. And I wanted to, the graph is a little bit washed out, but if you produce this on your computer, one of the dominating features of this graph is the gray background. And I don't know why Hadley Wickham decided that this was the best way to produce a graph, because it's full of what I think of as chart, just so much ink that doesn't help. And then also the distribution of the points. These points fall into 2 groups, the dark sky group and the light polarized group. And I want to emphasize that this is using default options in ggplot to make the point that just because you're using R doesn't mean that the result will be good. Do not assume that the default option is the one that produces the best graph. I mean, look at this, got too much ink. It's hard to tell where the groups are. These dots are too small. I can't hardly read these labels, and so on. So you're going to have to start learning some of the options if you want to make a chart that you would be happy communicating to other people. This is kind of a cool study. You know how moths are attracted to lights and so on. They just went to 10 different populations and collected moths, 5 of them where there's lots of lights and 5 of them where there's no lights. And they showed that the fraction of the male moths that are attracted to light differs between those 2 groups, as though there might be natural selection against the moths that go to light in those urban populations. 4, represent magnitudes honestly. Now this graph has a variety of things that I could just go on and on about. So I want to draw your attention to is the magnitudes. So I already mentioned the issue associated with using bars for quantitative measurements with standard errors. Come on, show the data. If it's possible, show the data. I think we can handle it. But the thing about bars is that the eye in the brain naturally takes the height of the bar to represent the magnitude, the value of the quantitative measurement along the axis. And so this bar here, to the eye, looks like it's about 4 times as high as this bar here. And the brain therefore expects this number to be 4 times that number, but it's not. It's not for 2 reasons. Well, it's not for one main reason, and that is there's no zero baseline. If you're going to use bars, it has to be a zero baseline, because that's the only way that bar height is going to represent magnitudes, honestly. So realizing that the zero baseline is key to a graph, what the authors did is they broke the axis here and then stuck the 0 on here, continuing the bar across the graph, but that didn't solve the dishonest magnitude problem. And what's a little bit silly about this effort here is that 100 is actually the baseline for this particular measurement. It's a slow wave sleep score relative to a control. And 100 is what you expect if there's no effect. What this graph is trying to show is that ducks, mallard ducks, are able to put half the brain to sleep at a time. And that's associated with whether their left eye is open and their right eye closed, their left eye is closed and their right eye open, or they're both open. So when they're both open, they're not asleep. When they're both closed, they're supposed to be around 100. So 100 is the sleep baseline. Eye stain. So labeling is also an issue here. It took me a while to figure out exactly what this referred to. So any one of us could do this. This is published in Nature. So just because it's in the glossiest magazine doesn't mean it's to a very high standard. So how should we? I'm going to talk a little bit about some of the basic graphs that we do and some tricks or some things that we can use to help improve the graphs and meet some of the criteria, some of the best practices that I described. So this is a bar graph, and a bar graph displays frequency. And this is about the only kind of data that bar graphs are useful for. Bar graphs are useful for showing frequency distributions, not quantitative measurements. And in a bar graph, the data are categorical. And so there's no particular order along here. And if you produce this plot in R, it will order them alphabetically. But it was already stressed in the presentation early, alphabetical is not necessarily the best way to order the categories. And the general recommendation is that the categories be ordered by their height. So start with the most frequent on the left and least frequent on the right, and order them that way, unless the variable itself has some natural order. If you were going to produce a graph of the frequency of use of all the letters of the alphabet in Shakespeare's plays, you would use a bar graph. My question for you is, would the categories be alphabetical in that case? Or should they go from E, the most frequent letter, all the way down to, I don't know what, Q, the least frequent letter? What would you do? Let's hear your opinion.
Alphabetical, because that's kind of the title and the goal of your graph, and we categorize alphabetical patterns a lot easier than what we would expect to see in the graph. For example, if Q was really high and if it was in the middle, we would still pick that out and say, that's very interesting. But if it was in the other way around, we might not make a lot of sense of it to categorize it, to have like E at the very beginning. I don't think our minds would like really understand the significance of that.
Does everybody agree with that, or is there a different perspective?
I think especially with letters that have similar frequencies, having it ordered from highest or most frequently used to lowest frequently used, it lets you compare better between ones that might appear and similar frequencies, whereas if it's organized alphabetically, trying to pick out letters that have been used a similar number of times is difficult because you're comparing.
I should have produced such a graph and then got your vote. I tend to fall on your side of this, and in part because the alphabet doesn't have a natural order, really. It's not a biological or cultural ordering. We just all know the same song, A, B, C. But I think it is easiest. Your eye goes straight to the commonest one, and you want to know what it is. What were people doing when they were killed by tigers in this park? And it also allows you to see how steep the distribution changes. Like the next category is far less tall than, and then it sort of, diminishes gradually. But a key for frequency distribution is that 0 has to be the baseline because you're using bars, otherwise the magnitudes are distorted. Now, there are other ways to display category frequency, and much abuse and defense has focused on the pie chart. So some people hate pie charts. I don't much like them, but other people like them. So both of these graphs are showing the same data, but which do you think gives the eye the most ideas in the least amount of time? Which do you think sort of meets tough days? What's that?
I would go with the boundary. Yes.
I would agree. One of the reasons that people actually study this, they do, get volunteers to sort of quickly visually estimate the magnitudes of each of these categories. And supposedly our eyes are better at visualizing not just relative but absolute magnitudes for the bar graph than the pie chart. It's the beads. It's hard for our eye and brain to see area as easily. Maybe if there's 2 categories, okay. So again, these are not necessarily hard and fast rules. You have to try them. And that's the beauty of computers, is that you can try them. You haven't, it's not 1867 anymore. You're not, painting a graph, and then once you've got your graph, you're stuck with it because you just don't have time to do it again. Histogram is like a bar graph, but for continuous data. And a key difference is that the bars run together because they really are continuous. The data themselves, and area matters more to the eye than height. Although the same thing when the bars are equal in width, but when they're contiguous, generally the eye is responding to area. Again, it's a frequency distribution, and 0 has to be the baseline, or everything is distorted. And then one of the choices that one faces is, how wide should the bars be? And so you can fiddle with that on the computer. Try wide, try narrow, which conveys the pattern more. This is a species abundance plot. So the frequency is the number of bird species falling into each of these different abundance categories in surveys of a natural monument in Texas. And the pattern leaps up at you. Most species are rare. And that's sort of the virtue of the graph. So now, how do you do associations between variables or differences between groups? So this is a grouped bar graph. That's usually what we do. We're looking at treatment effects. We're making comparisons. So this is a kind of graph called a grouped bar graph, and the data are malaria, the incidence of malaria in a bird, a great tit, in relation to an experimental treatment. So what the experiment involved was that researchers went to nest boxes where these birds were laying the eggs, and the control birds were kind of left alone. Their eggs were counted and everything. They were abused by the researchers, but in the treatment group, an egg was removed. 2 eggs were removed, and this caused the bird, the female great tit, to lay 1 more egg. So they were trying to stress the birds, make them exert even more effort than they would otherwise do, and then looking at the consequences for the incidence of malaria at the end of the nesting period. So make them work harder to make consequences. And so again, frequency is shown. It's a bar graph. There's a 0 baseline. And now there's 2 groups, the egg removal and control, and this displays the frequencies of birds, the count of birds falling into the two categories, yes had malaria, no did not have any undetectable malaria. So this is attempting to portray a pattern whereby in the control group most of the birds have no malaria, whereas in the treatment group there are about equal numbers, suggesting there might be a treatment pattern. And to help the eye keep track of the groups, we can see that this gap is wider than that. These are things that we can tweak in our. Another way of displaying the same data is using a mosaic plot. And I think of a mosaic plot as basically a visual representation of the contingency table, where there are two variables, the treatment variable at the bottom, and then the response variable at the side. And again, the bars represent frequencies, but in this case, relative frequencies. So they're all proportions. They sum to 1. And the width of the bar indicates the sample size. And in this case, they're relatively similar, so it doesn't belabor you too much. And if there's no difference between the treatments, then there'd be a line across here, and this would be as same size as this. But here you can see that the proportion of malaria-free birds is higher in this control group than in the equivalent group. So again, these are the choices now you have to make. There's more than one way to show differences between groups for a categorical variable like this. Now it's time for a vote. Which do you think, which of these two graphs do you think conveys best the differences or the effect of treatment on this experiment? Which makes you go, oh, most rapidly? So let's hear it for the mosaic plot.
I have a question.
Okay, good. Go ahead.
Is that yellow bar extending past the frequency on the y-axis?
It does go a little bit past, yeah. That's right. So it's more like 20, it's close to 30. Okay, how many for the mosaic plot? How many for the group bar graph? It's always the way, about half and half. So it's a real, but it will depend on what the data look like. Sometimes, especially if they're very different numbers in these groups in observational data, and I'll show you this in the lab on Thursday, the mosaic plot becomes terrible. But I find, especially when there are more than two groups, the group bar graph becomes visually very noisy. How about association between a numerical and a categorical variable? So differences between groups, essentially, in a quantitative variable. So this is an example that is from our book. It was a paper that was published in Science. And the paper was published to repeat an experiment that had previously been published in Science that had been labeled as chosen as one of Science's discovery of the year. And what the researchers had done is they had shown that, you can use light in the eyes to shift circadian rhythm. If you get jet lag, the best way to overcome jet lag is to go outside and just spend as much time as possible under daylight, under the new sunrise-sunset regime, and then you'll gradually reset your internal clock. And you can measure this by circadian rhythms of melatonin production. And so they carried out an experiment where they, woke people up and kept them in the dark, and then they woke them up at different times. And in one treatment shone light in their eyes. In the other treatment they shone nothing in their eyes. And in the third treatment they shone light behind the knees. And in the original experiment they found that shining light behind the knees was nearly as effective as shining in the eyes to reset the clock. And this was amazing. I mean, we do know that there are opsins in your bloodstream, so there are light-sensitive molecules. So how does that information get here? How was that transmitted? Anyway, people were skeptical about this. And so this was a paper that repeated the experiment and found no difference. And they criticized the design of the experiment. The way they designed the experiment, it's possible that the knee treatment was actually getting light in the eyes because of the actual technical features of the experiment. Anyway, in our book we include this, and we tried to have a caption for every data set that we used as an example in the book. And one day, Mike came up with the caption for this particular example in the book: "The knees who say night." So those of you who are Monty Python fans will know exactly what it is. Otherwise, forget it. This joke was so good that Mike started laughing to himself in his office, and then he got up and started to go down the hall and into everyone's office to tell them this joke, and he got no work done for the rest of that day. The caption was so good. Anyway, a strip chart is a very convenient way of showing the data. You can still add mean and standard error if you want, but I think this is a better way than the bar graph to displaying differences between groups. But it depends on how many data points you have. So here's a strip chart for measurements of hemoglobin concentration in men from a control US population and then 3 highland populations. And all 3 of these highland populations of people in Tibet, Ethiopia, and Andes have adapted to low oxygen at high elevation, but they do so in different ways. Apparently different molecular mechanisms are involved in adapting to low oxygen. One of the early results in this field showed that in the Andes, in South America, but only in South America, they actually have more hemoglobin in the blood. But this is accomplished in other ways in Tibet and Ethiopia. But here's a strip chart, and this is just a mess, so if there's too many data points, it becomes a problem. So it's not like strip chart is a universal solution. Another way of displaying the data is just showing 4 histograms, which I like a lot. It's pretty straightforward, but it's really key that these be stacked vertically rather than horizontally so that you can compare them, and that the axes are all of identical scale. And here's the same data in a box plot, and then another kind of plot that Mike likes, but I'm not so sure about, that's called violin plot. So violin plot is kind of like 2 histograms side by side, mirror image. So take the histogram, roll it over, and then smooth it somehow. So when it's wide, there's lots of data there. When it's narrow, there's few data. But it's smooth, so we'll attempt to connect all the data points, even if there are outliers. And you're all familiar with box plots, median and interquartiles and so on. Okay, I'd like to get your opinion so I can bring this to Mike. Not to weight your answer, but I'm gonna skip the strip chart because it's not very informative.
In the violin plots, is that dot the mean or the median?
I put the mean on it.
Okay, but you can choose.
I think you can choose, yep. Okay. How many like the violin plot better than the box plot? How many like the box plot better than the violin? Sorry, I didn't want to bias your choice in any way before I go talk to Mike.
It's the shapes, like, I don't know what the shapes are telling me. What's
I know, they make me almost uncomfortable.
Yeah.
Well, they show the distribution of all your data points across the population you take. They're used a lot in like energy.
Yeah.
Like flatworms or something.
I prefer, I think, this to the violin. I don't know, somehow. But again, there is some.
Can you show outliers in the same way with the violin plots? Or?
So nothing is identified as outlier, but you can imagine a modified violin plot that didn't try and connect all the dots with the data smoother, but actually stopped at some point, and then. But the basic algorithm for constructing a violin plot doesn't include that. You'd have to do some coding to get it. Actually, you know what? Somebody's already done this. You just have to find it on the web. But again, just do this to point out that there are choices to make, and you should try a few things, and then ask yourself, and ask others. Don't ask Mike. Which conveys which shows the data more clearly. It shows the pattern more effectively. You all know what a scatter plot is, so I don't really need to belabor it. But one thing I need to say is that a scatter plot's there to help you show association between the variables, how strong one variable is in its relation to the other. And that doesn't require zero baseline, because you're not trying to display magnitude here, you're trying to display association, correlation. This is, each of these data points is a comparison between how ornamented a father guppy was and how attractive his sons were to female guppies in the next generation. Because it's in R, someone came up with a modified scatter plot called a catterplot. And each symbol can be represented by a different cat silhouette. So you can be whimsical with R too, but don't waste too much time on it.
I think it's in the end.
It is.
What's that? What?
I don't know if I want to distract from the career like that.
It is totally distracting. It really serves no purpose whatsoever. In fact, it distorts everything. So a lot of the data that we analyze and display involve repeated measures of one sort or another. So by a repeated measure, I mean you take an experimental unit and you measure it multiple times, maybe in the spring and fall, like the same plot or the same individual. So when you plot the measurements made at 2 points in time, say, of the same sampling units, well, if you use a bar graph, it's going to break that little bit of information. But how do you include that bit of information? And one way to do it is to use a strip chart again, but a common convention is then to connect the dots with lines between the 2 points that belong to the same experimental unit. Sometimes those are called interaction plots. But I think the purpose of this by Weissenberger et al. Again was to show that all three of these have the same bar graph, and these different possibilities that give you different ideas, and so it's valuable to see the data points. So that you can see, for example, whether the dots are parallel, whether one individual or unit is just shifted up, or whether it's all over the place and complicated. If the data are paired, you have only two measurements, and another way of displaying them is to take the difference between them. And those differences are then behave as though you just have a single sample. And you can show that in a strip chart, such as this. So both of those are effective ways of presenting data that come in the form of repeated measures. So 3D graphs was brought up in the discussion, and here's an example of a 3D graph, and it has two strokes against it, more than two. One is it's a pie chart, and second, the pie is leaned over so that you can't actually see the areas. This is actually a fairly common trick in newspapers and so on. And the point came up as to whether there are different standards apply on blogs and other things where you're also trying to grab the attention of the viewer and get them to actually look twice. But we're biologists. We're already entertained. And I don't know who said it, but maybe it was Carl Brahman. A graph is meaningful only when the numbers are added. To tell you what the proportions are in each of those must be regarded as a failure. Put it in a table if the numbers are necessary. That's the only way to get this, see the pattern. Two-dimensional pies, again. And so, in my mind, there's questions are raised when you try to display data like this. So these are changes in different gas compositions between winter, summer, and this shows it yearly. And there's a natural tendency for researchers to use a graph or a table to stuff as much in as possible. as though it has to be all there. It's the only way you're going to be honest. But if the goal of, I mean, if you want to be totally honest, put it in a table, shove it in the supplement, and tell people to go there. But if you actually want to show a pattern, and the main pattern in these data is that these two gases changed in relative abundance from summer to winter. So there to there, there to there. That's actually not very easy to see when you first look at this graph. If the author wants you to see that pattern, then this is clearly not a very effective way of showing that. I look at that data and I'm not thinking, oh. I'm just thinking, whoa.
So would this pattern be more interpretable if we had just shown the winter and summer as pie chart?
I think so, yeah. Well, I put yearly in the same plot. If your main objective in showing this graph is to compare winter to summer. So these are all issues and decisions you have to make. A natural tendency is to stuff as much information as possible. But the question came up in the earlier discussion, is it okay to withhold information? Because am I withholding information on all these other chemicals if I just produce a graph that shows those two categories? Well, maybe if you did it in a bar graph, you'd be able to show them all. I don't know, give it a try. Otherwise, think about creating maybe a visually more detailed graph for the supplement, but then show the main pattern in the talk or in the main body, and point people to the full data set. Here's a graph from the book that we extracted and made from a meta-analysis that looked at whether marine reserves are actually effective in accumulating biomass of plants and animals. And so each of these data points that are shown in this frequency distribution is the ratio. So there's a pair of sites. One of them is the reserve, and one of them is outside of the reserve. And biomass ratio is the ratio of the total biomass of everything in the reserve, in the marine reserve, compared to the sort of the control or reference site outside the reserve. And so here are the values, and you can see that most of the values are greater than 1. But there is an issue with this graph, and I wonder, it's a little more subtle, but I wonder if anyone can detect it.
If it's a ratio, the scale shouldn't be like 0 through infinity, or it should level
Yeah, that's
over.
right. It doesn't truly represent magnitudes, honestly, I'd say. Because if you're greater than 1, you can go all the way from 1 to infinity, but if you're less than 1, you're crammed into this interval here, right? And so it does represent a kind of visual distortion of the effects. And so in that case, what would be more commonly done is log biomass ratio would be a way of changing the scales. So ratios can have issues and meet them all the time. The question came up in the discussion also, what do you think about tables? What are tables for? Well, one perspective is that tables are for stuffing all of your data in, so that anyone wishing to see what the numbers are could find them there. But I think that, if you're going to have a table in the main text of your paper and not in the appendix, that you should try, you're trying to show something, show a pattern, and tables can be used to illustrate patterns as well. And sometimes, not often, but sometimes a table might actually be more effective than a graph. And I think you should think about your tables and think about designing them in such a way that when the viewer looks at the table, they go, oh, rather than, what am I supposed to be looking at with all of these numbers? So the data set that I'm using as an example is a data set that was published in a cool paper in PLOS ONE comparing the inbreeding coefficients of Spanish Habsburg kings and queens in the survival of their progeny. So an inbreeding coefficient of 0.25, if brother and sister produce offspring, the offspring have an inbreeding coefficient of 0.25. If there were no inbreeding events further back than their parents. But you can get numbers in between as well. But anyway, there were something on the order of brother-sister matings in some of these families. And so what the author was interested in doing was comparing the inbreeding coefficients to the survival of the offspring that they produced. And these are detailed in history books. But even though all the numbers are here, it's everything you need. It's actually hard to see whether there's a pattern or not in these data, and there's no reason why the table can't be used to determine the presence or absence of a pattern. There's gaps between the numbers, and that just interferes with your ability to compare numbers that are sitting in a column. The variables of interest are like the ones over here and this one, so why are they separated by 3 other columns? And do we really need 3 decimal points? Like, come on, those are really hard to read and compare. So I've redrawn the table, and I put the F's, but now I sorted them from small to large, and then put survival, postnatal survival, in the column next to it. And now suddenly you can see, I realize there's not a lot of kings and queens, but nevertheless you look at that and go, well, that's pretty tantalizing. It looks like that postnatal survival was not great in cases of brother-sister mating or other situations where inbreeding coefficients were high. So think about tables as well, rather than just shove all the numbers in there. Graphs that allow you to manipulate the image. So that was pointed out as coming your way. And so more and more papers are being produced on websites and in documents where dynamic graphs are possible. And so you can slide your cursor over here and get the height of the line and the 2 values. And you can also, if you really wanted to zoom in on maybe one region and so on. So it's now possible to create graphs in R that can interact with the viewer if that is desired. Interactive scatter plots are also possible. So again, you have the opportunity of zooming in perhaps on particular sections or identifying particular points and what they are. So certainly interaction is becoming more and more possible. And graphs now that move are becoming more common. And here's the animated cube. You can ask yourself whether this is progress or not. But now it's possible to produce this and ask yourself, does this help me perceive the differences between these groups? But there's no reason why graphs need to be static or photographs, as Harry Potter has shown. What else? Oh yeah, so returning to the fact that history was my least favorite subject, I think maybe if graphs were used more. I don't know if any of you have ever seen this graph, the Atlantic slave trade in 2 minutes. So it's a graph, but it's a moving graph, and it's a movie. And what it shows is a timeline. I don't know if I can actually reduce the size of this to fit it all in. I don't want to make it too small. Right. So what this graph is showing is the number of slaves that were transported from primarily Africa to primarily the New World over time. So here's a graph which shows it. And the graph is pretty compelling already, especially when you read how many millions were shipped along the y-axis. But what this graph has done in addition is it's created a movie. So this dashed line is moving through time and showing also where the ship came from and where it disembarked. And so then the question is, does this help? Is this a better way, or is there a way in which we can use motion to display quantitative information like this? I'm going to let you, I think the size of the dot also indicates the number of slaves on each ship. So this is a cumulative number. Like, I took history when I was in high school, but it was pretty boring, I think, compared to this, because it gives you some idea of the scale of event, the scale of history. Can you see that, right? Mm-hmm. That's a lot of ships. And I guess it's memorable when you see it portrayed in this way rather than simply as cumulative numbers. So, and that's because, I mean, why do we make graphs? Our eyes and our brain are really good at detecting patterns. And where we find movies arresting. Netflix has made that absolutely clear. I like these amazing numbers. Also, you know, I constantly look for whether any ship docked in Canada, but I don't think so. So I was heartened by this. And I don't think there were any slaves transported directly from Africa to Canada. That doesn't mean they were slaves. Okay. I won't have time to show this. The Fallen of World War II. Have any of you watched this graph? So again, it's a graph of a movie. Highly recommend it. It's unbelievable. Okay, to finish, this is the paper we're reading for next week. Pseudo-replication and the design of ecological field experiments. And you can get it from the handouts tab on the course website. I need 2 presenters for next Tuesday. If you're interested, come on forward. And if I'm short, I need 2 presenters and 2 moderators. And if I'm short, then I will use R to randomly sample names from the class list. And you will receive an email from me today. Finally, before you leave, homework assignment number 1. Don't worry, it's not due to October, but don't leave it till October either. And it's the instructions are present in more detail on the homework page. And again, these are guidelines. They're not necessarily everything you want to do, but have a look at them. But here's the basic idea. I want you to find a bad graph published by your supervisor.
What if your supervisor is auditing your class?
Oh, better.
Yeah, that's great.
Analyze it.
Leticia's here.
Tell me why, think about all that we've discussed today and ask, according to what we think of as good principles, why does the graph not succeed as well as it might? Then I want you to get the data or simulate data if the data themselves are unavailable, and then create an improved graph in R. And leave yourself some room for improvement, like find a real stinker of a graph if you can. They're not that hard to find. And then analyze it. Why does it succeed? And then I want you to include your R script with assignment at the end too. Okay? Any questions?
So